Okay, so let's start. A battery has an electromotive force of 15 volts and an internal resistance of 2
We have
ohms.
visitors.
Hello. Who's the lucky one?
Come on, camera. Come on, camera.
Do you ever kill them?
Yeah.
She don't play tennis.
On camera.
Jeez. Oh, you just got recorded.
Yeah, we have a video plan.
Can you sign a waiver?
Okay. Let's see. Internal resistance of 2 ohms. What is the terminal voltage of the battery when attached to a circuit with equivalent resistance 70 ohms? Okay. So here is our EMF of 15 volts. Here's our internal resistance of 2 ohms. And after the internal resistance, that's where the battery begins. So this whole thing is the battery. Okay? Now this battery is attached to a circuit, whatever it is, with an equivalent resistance of 70 ohms. Okay? So we want to find the terminal voltage, the potential difference between this point right here and this point right here. Okay? So these dashed lines are completely imaginary. Okay? We can treat the circuit just like we normally do without the dashed lines. So this point connected to the negative plate. This point connected to the negative plate is charged to 0 volts. This point connected to the positive plate has a resistor in the way, so we need to figure out what the potential drop across that resistor is. To do that, we first find current. Okay? Finding current. So, total voltage, 15, equals current times total resistance, 72. What's my current?
0.208.
0.208 amps. Okay? So we're going to take that current and we're going to find the drop across the 2 ohm resistor. V equals 0.208 times 2. So what's the potential drop across that resistor? 0.4-ish. 416 volts. Okay, so that's the drop across this resistor. My total potential difference is going to be 15 minus the drop here, 0.416, gives me things.
Mr. Yarberry?
Huh?
If I did a different way, what I did was I treated the battery as like its own separate circuit and pretended it had that current. Then pretended like I didn't know the voltage, so I just did V equals IR with IR being 70 times 0.208. I got the same answer.
Okay. If you got the same answer, then it works.
Okay. But the right way to do it is...
Find the drop across the internal resistor.
Okay.
Anybody else have questions? Okay. So, part R. Part R is very, very similar. Find a general expression for the terminal voltage of the battery in terms of electromotive force. Okay, that's the symbol for electromotive force, this little squiggly epsilon. Huh? We got the same answer. Oh, that's good. Internal resistance and R equivalent. From this expression, state what happens to terminal voltage
as gets
larger. As R equivalent gets larger?
Yes.
Although my love I will not.
Yeah.
As R equivalent gets larger. I don't know why. I don't know how that backwards. Okay.
Which we love.
Then internal.
So I can actually keep the same.
There's only 12 of us today.
Hey, you want to come?
Nope.
Do physics with us? Okay.
No, he's stuck
Oh,
in
Margera.
So I'm actually going to keep the same diagram. Okay. Because my battery, that's my EMF. This is my R internal, and this is my R equivalent. Okay? Solve it exactly the same way. V, R EMF, equals I times R, where R is R equivalent plus R internal. Okay?
Then you take
Solve.
that I.
Right, solve for I. I equals
E over
R equivalent plus R internal. Okay?
Yeah.
take that, find the potential drop across our internal. So, potential drop is going to be this, I, times R internal. So, epsilon R internal over R equivalent plus R internal. Okay? So to find the terminal voltage, all it is EMF minus the potential drop. So V terminal equals EMF minus V drop, which is this stuff over here. EMF R internal over R equivalent plus R internal. Okay? And if you want, you can factor out a EMF to get 1 minus this times EMF. Okay? So, second part of the question, from this expression, state what happens to terminal voltage as gets R equivalent larger.
It becomes closer than EMF.
Yeah, it becomes the natural velocity.
Okay. Yeah, it slowly reaches the full EMF, right?
Yeah.
As R equivalent, this number right here gets larger and larger and larger and larger as it approaches infinity. This term goes to 0. So we get 1 times EMF. Okay?
That's exactly what happened.
That is exactly what
Believe it or
happened.
not, we have that same before.
Yeah, absolutely.
Good.
One more time.
Anybody have any questions?
I'm just kidding. We're not
Any
doing
tennis
homework
players?
today.
Huh? All right. So, real quickly, let's go over, clickety click, let's go over
Send them an email.
work, energy, and power for electric circuits. Okay? So the star of the show today is this equation. P equals IV. Power equals current times voltage. Now let me remind you of the definition of power. Power is energy per time.
What?
Yes.
Ah.
Okay? So power equals energy per time. If I have a current, okay, here's a battery, resistor, real easy stuff, V, R, okay? This is going to produce a current running through the resistor. That resistor is going to use up the energy of the battery, okay? What form is that energy going to take?
Electrical.
Well, it starts out as electrical in the battery. Then what does it go to?
Or light?
Whatever the resistor does, okay? Sometimes it's a heater. This could be a motor, so it's going to mechanical energy. It could be a light bulb going to light energy, okay? Whatever the resistor does, it goes from electrical energy to that sort of energy,
Yeah.
okay? Now, the rate at which it uses energy is given by this equation right here. Power is equals current times time, or no, voltage. Okay? So, P equals IV. Now, sometimes it's not convenient to write all this stuff. Like right here, I would have to solve. If I knew V is, I don't know, 10, and R is 75 and a half ohms. Billion ohms. Okay? So let's say I know V and I know R, and I want to find power. Well, I don't want to mess around finding current.
Yeah.
Okay?
Wouldn't it just be 10 over 75 and
Yeah, it would be, but that's too hard.
a half? Okay.
Okay. One thing I can do is substitute V equals IR into this equation. Okay?
I squared R?
So take the one you don't know, I, and solve for it. Divide both sides by R.
But isn't that what you just said you didn't want to do?
Yeah.
Well, this way I have a general term for it, so I can use it
Oh.
forevermore. I'm doing the work up front. Okay?
Gotcha. I see what you're saying.
And then put it in there.
I'm just
V
being
squared
silly.
over R.
Power is,
V
right,
squared.
V squared over R.
Over R.
Okay?
Mr. Yarber, you just came up with another equation.
I did. By
Or
combining two other equations.
I squared over...
Or I squared
We should
V.
patent it as the Yarber
Or
equation.
I squared R. I don't know what I'm saying.
Yeah, so you can replace the I, or you could replace the V. Power is V squared R. No, V squared. The other one.
I squared R.
I squared R. There we go. I'll get it right one at a time.
Oh,
Per.
Billy.
Per. Per squirter. Per squareder.
Tutor.
Pituitary. Okay. Anybody have any questions about power? Okay, so if I asked you, okay, if I gave you the voltage, if I gave you the voltage and resistance of like a light bulb, and I asked you how much energy that light bulb used in 5 minutes, what would you do? Guys?
V squared over R.
Huh?
I would use V squared over R.
Yeah, you would use V squared over R, but I asked you how much.
By 300.
Right, okay. If you're solving for energy, remember, power and energy not the same thing. If you're solving for energy, you got to use the other definition of power, energy per time, set them equal, and you're good. Anybody have any questions?
Yeah.
Yeah.
How come when other people are absent, we do this, and then when I'm absent to visit a college, we go over rocket science? That was the beginning of the end.
Bye, everybody.
Now! You learned rocket